Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Tinghui Zhou received his BS summa cum laude in computer science from the University of Minnesota and then went on to earn his master's degree in robotics from Carnegie Mellon University. Tinghui is currently a fourth-year PhD student at the Berkeley AI Research Lab under the supervision of Professor Alexei Efros. His research areas include computer vision, machine learning, and computer graphics, with primary focus on learning-based 3D visualization synthesis and understanding from 2D images. Tinghui, welcome to Data Skeptic.
Hi, thanks for having me.
I think a good starting point for our discussion would be to learn first about the problem you were solving in the paper. Can you describe your data set, which I believe is a collection of videos, and what you wanted to learn from that data?
The goal of this project is to teach the computer to understand the 3D geometry of the things it's observing and its ego motion during the exploration of the environment from watching unlabeled videos. In this particular case, we use this dataset called Kitty and the Cityscape. These datasets are basically like car driving in urban landscapes and then capturing the videos during its driving. The motivation of this problem setup is to sort of mimic how humans obtain the visual experience for learning about geometry. For humans, our visual experience solely consists of 2D image streams from moving around and observing the 3D world. So our hope is that by letting the computer watch tons of videos and try to come up with a consistent explanation of the visual world, it will become capable of geometric understanding like humans do.
Could we unpack that a little bit more? What do you mean by geometric understanding?
Like for humans, given a single image of, say, indoor scene, we're able to infer like its geometry, like the depth, ordering of the objects. Like we know some objects are in front of us and some objects are far from us, even from a single image. This problem is actually like mathematically under constraint if you want to solve it from a single image. The humans are able to do it because we have seen similar things, similar objects from the past visual experience, and we have built a consistent model of the 3D world.
Are you familiar with the technique forced perspective that they use in Hollywood movies sometimes?
I'm actually not familiar with that. Can you tell me a little bit about it?
So forced perspective is a kind of special effect, I guess. It's one of the earliest ones that were used in filmmaking. They used it a lot in the Lord of the Rings movies to make the hobbits look smaller proportionally to their, human actors that may have been more or less the same size in reality. You could put two actors on different planes, but orient the cameras so that they appear to be in the same 2D space, and then they can kind of act at each other to also be convincing, despite one person being, several feet back. And then, of course, you dress up the set, and it's a bit like an optical illusion. So this is an effect that can fool us. Our vision doesn't correctly assess the scene. But you could also think of another situation like a golf ball and a basketball being in the same 2D space and having the same diameters. But of course, you and I have outside information about the world. We know golf balls are much smaller than basketballs, so if they relatively appear to be the same size, the golf ball must be closer. So we see something that an algorithm wouldn't necessarily see if things like forced perspective were at play.
Right, exactly. So that's basically like a prior the humans have built from the past visual experience.
So it's interesting then, you and I as human beings, we bring that prior to the table, and your unsupervised system starts at a disadvantage because it doesn't have the training that you and I have had in our many years of living. How does that disadvantage work out? Does the system learn geometry in the scenes you've presented it?
I actually don't see it as a disadvantage. For us, we also don't have an accurate 3D sensor to know the exact 3D geometry of the scene we're seeing. We might not even have a very accurate ego motion estimation system in our brain. Even with this kind of setup, we are able to do this job very well. We are able to do this by purely observing 2D images. We don't have the sensors for accurate 3D geometry measurement. In our project, this is the exact same setup. The computer is only allowed to see 2D images or like 2D videos during training, and it is able to infer 3D geometry during testing.
Yeah, I think one of the more remarkable aspects of the paper is that it's unsupervised. Maybe to start with, can you tell me about the motivation for that design choice?
In our case, the distinction between supervised methods and the unsupervised method is that in supervised methods, you are typically giving deep neural networks supervision like depth measurements from some laser scanner or Kinect, or like ego motion signals taken from the car odometry. And in our case, we don't let the computer have access to these signals, and it should learn to do these tasks purely from watching 2D videos. Yeah, the main motivation is one is to mimic how humans learn from moving around, observing the 3D world, and second is that this allowed our system to be trained on more flexible setup, like more flexible data sets, like potentially in internet videos, where you don't have access to the 3D measurement from certain sensors.
Yeah, it does seem like there's a lot more unlabeled data available in the world than labeled data.
Right, exactly.
So, of course, the training does take place, though, then. Can you describe a little bit about the architecture of your network and how it gets feedback?
Our approach is largely inspired by the classical computer vision problem called image-based rendering or view synthesis. In view synthesis, typically you are given one or multiple views of a 3D scene, and then the goal is to synthesize other views of the same scene from different camera angles. Right? For instance, you're given maybe one view of the Eiffel Tower, and you want to be able to synthesize what it looks like from different camera angles. To solve this problem, one will first need to know the scene geometry as well as the relative camera poses between the input views and the target view. And then based on the geometry and the camera pose, the target view can be synthesized by basically projecting the pixels from the input views to the correct pixel coordinates in the target view. In order to do this task, the view synthesis task well, one needs to have a correct scene geometry and a camera pose inference modules. So in our work, we basically use deep networks as inference modules, and then formulate the entire view synthesis pipeline in an end-to-end differentiable manner that allows us to train the deep networks to do geometry and pose inference without any explicit labels, and purely using the task of view synthesis for supervision.
Let's take a break from our show and talk about our sponsor, Periscope Data. Periscope is the dashboarding tool for teams that lets you rapidly create charts from SQL queries. Let's be honest with ourselves here. If you're a data scientist, you've probably got some pretty impressive SQL chops, right? You go straight to the data to get your answer. But now, how do you visualize your results? Whether that's a quick histogram or a more elaborate dashboard, it's just a few clicks in Periscope Data. Sharing it is just one more click. And once you've got it done, it's done for good. Your collaborators can check back for an updated version anytime. No more follow-up emails asking for a refresh. No confused people looking at old versions of the data. Periscope Data solves all those problems for you. You can check it out for yourself at periscopedata.com/skeptics. One more time, that's periscopedata.com/skeptics. Am I correct in saying that essentially you're trying to predict the next frame or maybe one or two frames later, and that's where the loss function can kind of measure its accuracy?
Yeah, that's one way to put it. Basically, you try to predict what the scene will look like in other frames based on the predicted geometry and the camera pose. So if your estimation of those geometry and the camera pose are correct, then you will be able to do this frame prediction very well.
I think it's a very novel approach. I like the way that the network is set up and the architecture, and we'll actually get into some more of that in a few questions. But I was curious about the nature of some of the training data. Well, I'm a little bit familiar with Cityscape, so I've watched some of the contents of that corpus, and I know that the average car driving down the street, it is somewhat predictable from frame to frame, but there are also unpredictable things, like a bird flies through, or you make even a left-hand turn kind of introduces a lot more new information than driving straight. How does the network function in cases where, there are moments when the frames are very predictable, but other times when, independent of the learning, the scene is a little bit more dynamic?
You mean like when the scenes have moving objects?
Yeah.
Yeah, that's a very tough problem to tackle right now. And in our paper, we basically have these mechanism for predicting whether a particular pixel has a moving object or this pixel will be occluded in the next frame. things like that. We call it the explainability prediction. So basically, we try to let a network not only predict scene geometry and camera pose, but also predict whether these pixels could be explained in the next frame or the nearby frames purely using the view synthesis formulation. So by factoring these into account, we could have a more robust system. Like the network could be trained in a more robust way when there's moving objects or objects being occluded, disoccluded in nearby frames.
Yeah, just to double check, in case some listeners aren't familiar, can you give a rough definition of what occlusion is and why it's such a problem in tasks like this?
Occlusion basically means that so you have some object that you can observe in the current frame, and then when you move to a different camera location, this object might become occluded by another object that is in front of it. For instance, suppose you have two objects, one is in front of the other. The second object is currently occluded. Many of its pixels are currently not visible from current camera viewpoint. But when you move it to, for example, the agent has moved to the side, the pixels become disoccluded because now the depth ordering between these objects have changed. Then those pixels will become visible again or disoccluded.
Yeah, it's definitely an added challenge for a computer vision researcher for sure.
Because in our formulation of using view synthesis as the training signal, this is particularly problematic because we basically, the view synthesis formulation assumes that all the pixels in a target frame will also be visible in the nearby frames. We need some mechanism to explicitly model this occlusion or dynamic object effects.
Can you tell me about how that's built into the network architecture?
So basically, we have an additional branch of the network that predicts whether this pixel in a target frame could be explained by the view synthesis formulation. So here, the explainability encodes a lot of factors such as dynamic objects or occlusion or reflections. So all these factors cannot be explained by our view synthesis formulation. So by predicting these masks, we then can weight the loss function based on this explainability. Basically, when we train a network, if it believes that some of the current pixels are not explainable by the view synthesis formulation, then we will not try to get the gradients for training from those pixels. So these basically have a robust way of dealing with those unexplainable factors while still being able to train using the view synthesis formulation.
Yeah, I thought that was a really novel approach to doing this. I like that aspect of the paper. Every so often we bump into problems on this podcast because it's an audio show and we can't obviously have visuals. So I will definitely direct people to look at your paper, which will be in the show notes. But maybe for those who can't do that because they're driving or whatever, can you just describe what the explainability mask looks like when mapped onto an image? Because I found that the visuals you had in the paper were very helpful in me understanding what the explainability mask was.
So in this cityscapes dataset, it's a car driving dataset, and you see pedestrians walking in the streets. In our case, the explainability mask, when it sees pedestrians walking, it will be able to tell that, these are the dynamic objects that are not explainable by the simple depth-based view synthesis formulation. Also, another example would be things that are visible in the target frame but become invisible in the nearby frames because the car has moved. So those pixels will be masked as unexplainable as well. But we also see some other factors that we do not quite understand why the network decides to mask them as unexplainable. It's not just doing the dynamics and occlusion, it's also learning some other factors which we somehow cannot interpret them very well right now.
Yeah, but nonetheless, it's an unsupervised approach. So the fact that it works at all is almost amazing to me on some level. And I thought that was a novel introduction that you would then be able to weight the loss function based on. You're almost filtering out the things that are too dynamic or chaotic. Is that the way you guys look at it?
Basically, the motivation is to improve the robustness of our learning pipeline to those factors that cannot be explained by the view synthesis formulation. by waiving the gradients based on like explainability mask, you'll be able to filter out those noisy signals so the network could learn to do those tasks you're interested in a more robust way.
I'm curious about how you see this potentially fitting into a driverless car scenario. How would a system like that be able to benefit from the research you've done?
For self-driving cars, for instance, they would need very accurate and very dense geometry reasoning capabilities. Currently, most driving cars are basically using these LiDAR sensors, and usually they only give you sparse point clouds. So with this approach, potentially you could try to densify sparse point clouds obtained from a LiDAR sensor with our approach. And also, our ego motion estimation module turns out to be pretty accurate compared to the traditional approaches like SLAM. SLAM is short for simultaneous localization and mapping. In addition to the geometry, also provide estimation for the camera pose or the trajectory of the cameras. So those could also be very useful for the self-driving scenarios where you want to know exactly where the car moves.
So as you'd mentioned, the self-driving car has a lot more telemetry available than a typical scenario. It has the LiDAR and maybe some other auxiliary systems, mainly because it's so important that the self-driving car know exactly what's around it in order to provide safety. But there are other applications like, as you had mentioned, like YouTube videos, where you generally do not have any LiDAR data or any 3D information as well. Now we're in a scenario where your methods may be applicable, whereas what's developed in self-driving cars could never apply there. I was curious if there's any specific areas or applications you were excited about taking this research.
Being able to do single view geometry reasoning has lots of applications. For instance, when you take a selfie, you want to be able to add like depth effects to the portrait you just taken. You can already see these effects in iPhone 7 or iPhone 7 Plus. Basically, you could try to focus the image in the foreground portrait instead of the background automatically. And with our approach, like if it's able to train and work well on general internet videos, then you can basically refocus your photos based on the predicted depth to give you a more visually compelling effect. Another application might be to basically reconstruct the 3D scenes you have captured.
Yeah, so if the system is able to train and work well on just general videos, you will be able to sort of reconstruct different objects, different scenes, maybe like have some sort of VR application where you can basically like let the user to move in different camera angles to explore the scene from many different viewpoints to have a sort of an immersive experience.
Obviously, your technique has some disadvantages compared to like the self-driving car example I keep going back to, because they have LiDAR and all these other supervised features available. So it makes, if you could even get close to their results, it would be massively impressive. Could you tell me a little bit about the benchmarks you described in the paper?
So we compared two types of approaches. One is the method that uses laser scanner measurements at supervision to train this depth estimation system. The other one is a more recent approach that doesn't assume depth, but assumes registered cameras. So in this setup, there's stereo cameras capturing stereo videos during training, and then you do single view depth estimation during testing, just like in our case. So we are comparable to these approaches. We compare to some of these approaches, but we're definitely not state of the art in these single view depth estimation task because of the unsupervised nature. I think one particular paper that shows quite impressive performance is this paper by Clement Goddard. Paper title is Unsupervised Molecular Depth Estimation with Left-Right Consistency. So they assume stereo cameras during training, but also just does single-view depth during testing. I think there's still some improvement to be made to be able to reach layer-level performance, but I'm pretty excited about being able to just train on general videos. Yeah, being able to allow the system to watch general videos and have the capability of doing geometry and pose inference.
Maybe to wind up, I'd love to go through some questions about the general architecture of your deep learning network. Can you describe, not just, a little bit about the convolutional layers and that sort of thing, which of course are interesting, but also how you guys came to the decisions you made about how to architect it?
One critical decision we made about architecture is to have multi-scale predictions. By multi-scale, I mean the images, when we make the prediction, it doesn't just output per pixel depth in the original input image scale, but it also predicts the depth in the image that is resized to a smaller scale. By doing this, you're able to derive gradients in a larger neighborhood of image pixels. Yeah, basically the motivation of using multi-scales is to allow the gradients to be propagated from a larger neighborhood to facilitate the training of the network.
Can you tell me a little bit about the general architecture? How many, convolutional layers did you have? How long did it take to train? That sort of thing?
We basically adopt architecture from another paper. Nowadays, it's called the UNet architecture, where you basically connect features extracted in lower levels to higher levels when they do the prediction. So the UNet is basically also like the skip architectures people use from before. The motivation is to be able to get finer predictions by utilizing lower level features instead of just higher level features that might have abstract away too much details.
So I wanted to wind up by asking, what's next for this line of research? Do you have some further steps, or was this kind of the conclusion to some work?
I'm interested in exploring more in this direction, in particular to be able to explicitly make estimation about the dynamics. Currently, we just have a mask that couples everything together and have just output a per pixel prediction of whether it's explainable or not. It would be nice to actually be able to factorize these components into more explicit predictions. We would be interested in being able to have more explicit estimation of the dynamics of the scene. For instance, we want to infer the motion of the pedestrians, where they are moving and how fast they are moving, or the cars on the streets. So this could be very useful for self-driving applications where you really want to understand not only the geometry but also the dynamics as well.
No, I think this is really interesting. I especially like that it seems to be, even though, my initial attraction was like, oh, let's learn more about how this can apply in self-driving cars. What I was pleasantly surprised to learn is that this, as a technique, has much more wide and general use cases available. So I'm very eager to see where the line of work goes.
Yeah, we're excited too.
Is there any place people can follow you online, on Twitter or a blog or anything like that?
So there's one thing that we're going to launch very soon, which is blog, like official blog by Berkeley AI Lab. We're going to have blogs about the research done in our lab. This paper will be one of the first few blog posts.
Well, fantastic. I'm looking forward to seeing that. Be sure to let me know. I'll share it on our site and our mailing list when it comes out.
Yeah, that would be great. Yeah, I definitely will keep you posted.
Excellent. Well, Tinghui, thank you so much for taking the time to come on and share some details about your work with the listening audience. I think it's a really interesting paper, and I'm glad we had a chance to chat about it.
Yeah, thank you very much for having me. Yeah, it's very nice talking to you.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.